Today, we're diving into a really cool piece of aerospace engineering that tackles a huge puzzle. How in the world do you keep a billion-dollar satellite pointed in exactly the right direction, especially when a critical part fails? Millions of miles from the nearest mechanic? I mean, just stop and think about that for a second. You've got this object hurtling through space faster than a bullet, and it needs to point its camera or its antenna with absolute pinpoint accuracy. We're talking about hitting a tiny target thousands of miles away without the slightest shake. It's an absolutely incredible challenge. And that, right there, is the heart of the problem we're digging into. What happens when the machinery that does all that precise pointing breaks? This is where a little bit of smarter math comes in, and honestly, changes everything. So the official term for all this is attitude control. It's really just a fancy way of talking about which way the satellite is facing, its roll, its pitch, its yaw. And getting this right is absolutely fundamental to pretty much any space mission you can think of, from your daily weather forecast to exploring the deepest corners of the universe.
All right, so let's get into the specifics. How do you steer a satellite when it's lost one of its main steering tools? This is a classic problem in aerospace, and the solution we're about to see is just really, really clever.
So inside most satellites, you've got these things called reaction wheels. You can just think of them like super precise internal gyroscopes. By spinning these wheels faster or slower, the satellite itself can pivot in the opposite direction. It's all thanks to Newton's third law. For every action, there's an equal and opposite reaction. And you need at least 3 of them to control all 3 axes of rotation. But here's the multi-billion-dollar question. Reaction wheels are mechanical parts. They have bearings, they have motors, and eventually they can fail. So when one of your 3 wheels just stops working, you suddenly have a massive problem on your hands. You've effectively lost control over an entire dimension of movement.
In engineering speak, this is what's known as an underactuated system. And that analogy of a car that can only turn left or go straight, it's perfect. Sure, you can probably still get where you're going, but it's going to take some incredibly clever, non-obvious maneuvers to pull it off. You need a much smarter driver, or in this case, a smarter control system.
And this brings us right to the breakthrough. Researchers came up with a new method, and it's got a mouthful of a name. Linear Time-Varying Fractional-Order Model Predictive Control. Yeah, let's just call it LTV-FOMPC for short. But don't worry about the name. The idea behind it is the real aha moment here.
Okay, so this is the absolute key to the whole thing. The old way of controlling these systems, it pretty much only looks at the pointing error right now and reacts to it. It has a really short-term memory. But this new way, it uses something called fractional order math, and the game changer is that this math has memory. It doesn't just see the error in this instant, it considers the entire history of past errors, which lets it make way, way smarter adjustments for the future. And this diagram here shows us how it all fits together. You start with your target, the desired orientation. The satellite sensors are constantly measuring where it's actually pointing. Now, all that data flows right into that LTV-FOMC controller. That's the brains of the operation. And using that special fractional order memory of all the past mistakes, it calculates the absolute best, most efficient command to send to those 2 remaining wheels.
So, that's the theory, right? Sounds great on paper. But does it actually work any better? Well, the researchers ran a head-to-head simulation, pitting this new method against the traditional one. And, well, the results are pretty staggering.
First up, speed. How quickly can it get the job done? The new method, with its smarter math, was able to get the satellite reoriented and locked on target 80% faster. That's not just a little better, that's a massive leap forward, especially when mission time is critical.
Okay, next up, efficiency. Look, being fast is great, but not if you burn through all your power to do it. And this is where it gets even more impressive. The new method got there 80% faster while using 67% less torque. That means 67% less energy consumed, which is absolutely vital for extending a satellite's lifespan. This chart just makes those energy savings crystal clear. On the left, you see the total torque. That's the muscle the wheels had to use for the old method. And on the right, for the new method, it's significantly lower. It is literally doing more with less.
And finally, we get to what might be the most important metric of all, accuracy. Because getting there fast and efficiently doesn't mean a thing if you're not pointing at exactly the right spot in the sky. Well, the new method crushed it here too, reducing the average pointing error by over 80%. It's not just faster, it's also dramatically more precise. And here's the raw data to prove it. You don't have to be a rocket scientist to see the difference. Just look at the pitch row. The error with the old method was over 3.2,
With the new method, it's down to just zero 0.4. I mean, across every single axis, the improvement is it's huge.
So, okay, the numbers are obviously impressive, but what does this all really mean in the real world? What are the actual consequences of this innovation for the future of space tech?
Well, it has 3 huge impacts. First, it makes our satellites way more robust. A mission doesn't have to be a total loss just because one wheel fails. Second, it could actually make satellites cheaper. Maybe future designs don't need 3 or 4 wheels. Maybe they can be designed to work with just 2 from the start, saving weight and launch costs. And third, it means longer lifespans. Using less energy and putting less strain on the parts means these incredible, expensive assets can keep working for us for much, much longer.
You know, the researchers themselves summed it up perfectly. This isn't just some small improvement. It's a completely new and highly effective approach that, in their words, surpasses existing methods in every important way. Performance, speed, efficiency, you name it.
And that really leaves us with a fascinating thought to end on. This whole massive leap forward was made possible not by building a better piece of hardware, but by applying a different, smarter type of math to an old problem. It really makes you wonder, what other huge breakthroughs are just sitting there, waiting for us if we just find a smarter way to do the math?